Hi, everyone. I just posted Dr. Perry's worked examples series 1, part 1. These are going to be very helpful when you start working on problem set 1. I am going to post more of these worked examples, series 2, 3, 4, and then each series is going to have 2 parts. Starting with series 1, I thought that actually I go over at least some of these questions and some of the solutions and explain them. Please study the rest of them, the ones that I'm not going over. So study those. Let me know if you have any questions. Starting with the first question, express the concentrations, pressures of the following atmospheric constituents in each of the units: atmosphere, mole per liter, molecules per centimeter cubed, and ppmv, which is the mixing ratio, but the volume mixing ratio. And we've got now this question has 4 parts: oxygen, carbon dioxide, methane, and hydroxyl radical. We're going to use these units and use these numbers in the calculations later on in the course. So it's better to understand and learn. I'm sure you already know most of these. How to convert, it's better to learn how to convert from one unit to another. And when we become comfortable in this, then we can do more complicated calculations. Starting with part 1A, oxygen. P is 0.21 atmosphere. By the way, actually, I need to add that in the exam, I will give you enough information. So 2 most important information that I should provide right at the beginning is T. We are going to use 300 Kelvin for temperature, and for total pressure, we are going to use 1 atmosphere. So these 2 important information, important information will be given in the exam. All right, starting with oxygen. So the pressure is given in atmosphere. So what we want is to convert it to mole per liter, to molecules per centimeter cubed, and ppmv. Mole per liter, we are already familiar with this. Mole per liter is the concentration unit. So concentration, remember, concentration is always mole per liter. Moles or mole per liter or volume. So it's better actually to use the general equation. So it is always number of moles per volume. In this specific case, it is the volume is expressed in liters. All right, to convert that, we can use a very important and, of course, simple equation that we have. I need to actually switch between the equation sheet that I posted on Canvas. So it is on Canvas. This is the equation sheet. All these equations and all these unit conversion factors will be given. Okay, so you will have all these in the exam, and also this electromagnetic spectrum. I will explain it when we talk about radiation, and this table as well for humidity calculations. But these equations are given, including the ideal gas law, PV equals nRT. So this equation is given. All right. PV equals nRT, and I'm going to use it in this calculation. Why is that? So PV, if I show you quickly here, PV is equal to nRT. I can rearrange this equation in this form. So if I divide both sides by V, it is N over V RT. And then if you rearrange it, you will get this equation. You rearrange that, okay? So N over V, which is concentration, is P over RT. Now, the important thing is the units, okay? We need to make sure that the units match, and then at the very end, we get the unit that the question wants us to. Okay, so mole per liter is important. Pressure is the pressure of oxygen. Of course, it's the partial pressure. Look, the total pressure is 1 atmosphere. That's the partial pressure of oxygen. Okay, that's the partial, and the information is given here. Partial pressure of oxygen is this value. We just plug that value into this equation, 0.21 atmosphere. And then the temperature in the ideal gas law, must be in Kelvin. So sometimes we might give you the temperature in degrees Celsius. Make sure that you're converting it to Kelvin. So that is in Kelvin. And you just plug that value into the equation. And then what we want is the R value. Look, if I go back to the equation sheet, so let's go back to the equation sheet. We've got two different values. Sometimes we might have in the exam, I might give you more, but look, we've got two in this equation sheet. We've got two different values for the gas constant. They are different because their units are different. One of them is in liter atmosphere per mole Kelvin. So if I show you here, so it is liter atmosphere per mole Kelvin, so over mole Kelvin, right? And then the other one is joules per mole Kelvin, so joules per mole Kelvin. The good thing about both of these is that, so look, in terms of the number of moles, we only have moles. In terms of temperature, we have Kelvin, so we don't really need to worry about those. The only parts that actually are changing in terms of units are volume and pressure. In joules, for joules, actually, the volume is in meter cubed, pressure is in Pascal. So we need to make sure that actually they match, and they are the units that we want when we use, for example, this number in the calculations or this other number in the calculations. In this specific case, in part 1A of this question, look, the pressure is given in atmosphere. So what we need for pressure in terms of the values that we're using for R, we need it to be in atmosphere. So which means that we can use this one. What about the volume? We can use this number. But what about the volume? The volume should be in liters. Look, we want to convert it to moles per liter. So that's great. If we use this value, we have both the units that we want for the pressure and volume. So we're going to use that value in here. If you plug them into this equation, please do this calculation. So it should give you this value, which is, in terms of units, should be in mole per liter. That is the concentration, right? Because concentration was N over V. So this mole per liter, remember, from first year chemistry, we remember this, it is concentration. All right, the second part of the question wants us now to convert that or the oxygen that is given in partial pressure. It wants us to convert it to molecules per centimeter cube. Molecules per centimeter cube. How to do that? So we already converted that pressure to concentration, moles per liter. Now we need to convert that to molecules per centimeter cube. So going from moles to molecules and over liter to over centimeter cube. So liter to centimeter cube. How to do that? So we're going to do that step by step. This is exactly the same number here. So I just copied it down here. And then we can easily convert moles per liter to molecules per liter using the Avogadro's number. So you've got Avogadro's number. So Avogadro's number is here in the equation sheet. What is the meaning of that? It means that we've got 6.022 times 10 to the 23 molecules per mole of a substance. For example, in this case, we've got gaseous oxygen. So every mole of gaseous oxygen, or oxygen in this case, contains this number of molecules, every mole, okay? So we can use that now. It's a conversion factor per 1 mole. So in every mole, in 1 mole of oxygen, we've got this number of molecules. We set it up this way. Why? Because we want to these 2 moles to cancel each other, and what we want at the very end is just molecules per liter from this part of the calculation. So if you multiply this number by this number, it should give you that concentration in molecules per liter, okay, per liter. But now we need to convert that liter to centimeter cubed because we want it to be in molecules per centimeter cube. So we need one more step. Okay, so do we have any conversion factors here that can help us? Look, it's here. So we've got for 1,000 liters, we can convert it to 1 meter cubed, and then 1 meter cubed, we can convert it to 1 centimeter cubed. So this is given in the equation sheet, which is great. So we're going to use that. Here, actually, it has been done a little differently. So what is done here is that first liter was converted to milliliter, and we know that 1 milliliter is 1 centimeter cube. How? So 1,000 liters, let me show you, 1,000 liters is equal to 1 meter cubed. The question is, how many centimeter cubes are in 1 liter? So we've got 1 liter, we're going to convert it to centimeter cubed. How to do that? Okay, so first we convert this using this conversion factor. We convert that to centimeter cube. So 1,000 liters, 1 meter cubed. So we set this up in a way that these two cancel each other, and what we're left with at the end of this step is just meter cubed. Okay, so we set it up in this way, and then look, you have to do it this way. The second conversion factor, cubed. In every 1 meter, we have 100 centimeters. In every 1 meter, we have 100 centimeters, and both of them are cubed. Both of them are cubed. What does this mean? So if I do the calculations now, so it is 1 divided by 1,000, this first step, to give me the that value in meter cubed. So 1 over 1,000 meter cubed multiplied by, in every 1 meter cubed, we've got 100 to the power of 3 centimeter cubed. Okay. So 1 over 1,000 meter cubed and meter cubed cancel, times, this is 10 to the 6. Let me know if you have any questions about this. Or 1 million centimeter cubed. Therefore, it should give us 1,000 centimeter cubed. So 1 liter of a substance is 1,000 centimeter cubed. All right, now if I go back, look, it's the same as this, right? It was done a little differently, but let me know if you have any questions, okay? We can discuss it during office hours or right after class. So look, it is the same as that. 1 liter, 1,000 centimeter cubed. So you just need to cancel those milliliters. And then if you do these calculations at the very end, so mole and mole cancel each other. Now, liter and liter cancel each other. So in terms of units, what we're left with is molecules over centimeter cubed. So these are the two only units that survive in this set of steps, right? In this set of steps in the calculation. All right. So we end up with this value. Please do the calculations. Make sure that this value is correct. Let me know if you have any questions. But probably the easiest way, because I just used this conversion factor from the equation sheet, probably this was easier. Actually, we could do this on the side and then use that conversion factor in every liter. So this conversion factor, 1 liter over 1,000 centimeter cube. This conversion factor, we just could use it directly here, okay, instead of, for example, using these two. All right, here is the this value, this pressure in terms of molecules per centimeter cube. All right, this second part or third part might be a bit confusing, so I am going to do it in a different way. Very similar, but a little different. I'm just going to use the equations that we already have in the slides. So in order to go now from pressure to ppmv, that is the volume mixing ratio, it's simple because we already have the equations in the slides. You remember, so pi over pt is equal to vi over vt, volumetric ratio, right? The ratio of partial pressures, or the ratio of the partial pressure of the molecule over the total pressure is equal to the volume mixing ratio, right? This T refers to total, okay? All right, so we already have this equation. Now we're converting from pressure to ppmv. How to do that? Okay, so VI over VT, therefore VI, which is, in this case, I is oxygen, V oxygen, over V total. We want it to be in ppmv. It is equal to, so it is equal to P oxygen, partial pressure of oxygen, over total, which is equal to 0.21 atmosphere over 1 atmosphere. So I show you, I show it over here. So 0.21 atmosphere over 1 atmosphere. Okay, just show it over here. Okay, so if I just use these two values and then divide them by each other and then report it as the value for ppmv, then what I have here, look, I have 1 part of that unit, which is 1 atmosphere, over 1 part. I can't really use this ratio as ppmv, because ppmv, or ppm in that unit, means parts, or part per million parts, 1 million parts. But in the denominator, I only have 1 part. So I have to convert that 1 atmosphere to 1 million atmospheres. So I have to do that to be able to get the volume ratio in ppmv, in part per million. In order to do that, what I need to do is to multiply both the denominator. So let me do that here. Let me erase these. Multiply both the denominator and the numerator by 10 to the 6. Why is that? 10 to the 6 means is 1 million. Okay, because in the denominator I need 1 million atmospheres, but I cannot just multiply the denominator by 10 to the 6. I need to multiply this whole thing by 1, because that's the only way to keep this number the same and not change it. But at the same time, because I needed 10 to the 6 in the denominator, I have to multiply 10 to the 6 by the numerator as well. Look, 10 to the 6 divided by 10 to the 6 is just 1. So it's a trick that I use here. It's a trick to be able to make that unit that I want in the denominator, but at the same time to not change this whole number. I don't want to change it, because if I change it, then the final value that I will obtain is going to be wrong. So that's why. So now in the denominator, look, so now we have here, I'm so sorry, actually, I just wanted to show you everything on this page. So now in the denominator, I have this value, 1 times 10 to the 6 atmosphere. I still have that 10 to the 6 that I need to multiply this whole thing by. I still have that value. But look, in the denominator, at least I made that 1 million atmospheres. So look, it is now 0.21 atmosphere over 1 million atmospheres. So part per million still have 10 to the 6. So now I have part per million, which is great. So Whatever this number is, 0.21 times 10 to the 6, you can report it as the value 21 times 10 to the 6 is the value for the volume ratio, but now in parts per million. Please let me know if you have any questions about this.